So is it visible, the screen?
Yes, sir.
Okay, so first, this is the actual syllabus for algorithm. So first we have to learn the asymptotic notation, how to analyze an algorithm, given algorithm. Okay, and then solving the recurrence relation, how to solve the recurrence relation. There are three techniques. First one, very first one is the substitution method, then the recurrence tree, and then finally the master theorem. Master theorem is very restricted way to solve recurrence relation. First, we have to design the algorithm. Then we have to then we have to find out the recurrence relation of that particular algorithm to get the asymptotic notation, to get the complexity of the algorithm. Okay, and there are some design techniques. First one is your divide and conquer design technique, greedy algorithm, dynamic programming, backtracking. Okay, and mainly the graph. This graph data structure, the algorithm associated with this graph data structures are to find the problems, the single source shortest path problem. For this particular problem, we have to use the Bellman-Ford and Dijkstra, where Bellman-Ford use the dynamic programming, Dijkstra use the greedy approach. All pair shortest path problem, we have to use the Floyd-Warshall algorithm. And in case of greedy, the spanning trees are there. We have to use the Primes and Kruskal's algorithm, job scheduling with deadlines, fractional knapsack, and the 0-1 knapsack. This belongs to the dynamic programming approach. Okay. In greedy, there is another algorithm, Huffman coding. We know the graph traversals, depth first search, breadth first search. In case of dynamic programming, the matrix chain multiplication, longest LCS, longest common subsequence between two strings, 0-1 knapsack. In case of backtracking, 8 queens problem, graph coloring problems are there. String matching algorithm, there are Knuth, Mori, Spratt. This algorithm is very popular. And maximal flow, for maximal flow in a given network, that is in a given graph, we have to find out the maximal flow. uh, Maximal flow for finding, we have to use the Ford Fulkerson algorithm, and some NP, NP complete, NP hard, and some shorting algorithms are there. So these are the syllabus for any uh, algorithmic course. So first, let us start with the asymptotic notation. Okay. So first of all, let's do it 1 second. So first of all, what do you mean by algorithm? An algorithm is a finite sequence of unambiguous instruction for solving a problem. Okay. So it is a set of instructions to solve a particular problem. Okay. Do you know the characteristics of algorithm? There are 5 characteristics of an algorithm. Any idea about 5 characteristics? To become an algorithm, we have 5 characteristics. Is it visible, the screen?
Yes, sir.
Sir.
Okay, so first of all, the algorithm, it is a finite set of instructions, unambiguous instruction to solve a problem. Okay, so there are 5 characteristics for algorithm, that is input, that there must be 1, 2 or more inputs for an algorithm. Second one is the output, but this output should be only one output will be there, at least one quantity is produced. Okay, next one is definiteness. So definiteness means So algorithm is a finite sequence of unambiguous instructions. So this instruction should be unambiguous and clear. That is definiteness. This algorithm is definite. Your instructions are unambiguous, and clear enough. Finiteness, that is, if we trace out the instructions of an algorithm, then for all cases, your algorithm terminates after a certain number of steps. That is your finiteness. Your algorithm is finite. And effectiveness, your algorithm is very basic. Okay, your algorithm is very basic enough. That is a person can execute your algorithm with just pen and paper. Your algorithm is very effective. That is, it is very basic enough. So these are the properties or characteristics of an algorithm. Okay. So these are the characteristics. Okay. Every step should be very basic enough to understand and can be implemented using any programming language. That is effectiveness. Finiteness, after certain number of steps, it will terminate. Okay. And for finding the complexity of an algorithm, we have to use the asymptotic notation. Okay. So do you know the difference between program complexity and algorithmic complexity? Any idea? Algorithmic complexity, this is solved by asymptotic notation, whereas your program complexity cyclomatic complexity. Cyclomatic complexity. Have you heard the term the cyclomatic complexity in software engineering?
Yes, sir.
Okay, so asymptotic notation is used to find out the time complexity of your algorithm. That is running time, how much time it will take in terms of your input size n. Okay, this is asymptotic notation. Whereas cyclomatic complexity is different. It is mainly used for program complexity. Okay, so for cyclomatic complexity, there are three techniques. First one is the cyclomatic. How to find out the cyclomatic complexity? There are first one that your cyclomatic complexity of, so first of all, your program, any program is given. Okay, any program is given. This program may be written in C, Java, C++. Okay, so first of all, you have to find out the control flow graph of the given program. Next, that is control flow graph CFG. So for that CFG, your cyclomatic complexity will be your E minus n plus 2. This is first formula. Your second formula is the number of predicate node of the graph, plus 1. The third formula is, what is the third formula? Third formula is the number of closed region of your graph, plus 1. Okay. So these are the three techniques for finding the cyclomatic complexity of your control flow graph, that is of your given program. So let us check. If block. So for if block, how to find out the control flow graph for a if block? This is A. Okay, A is the node. It denotes the if block. So for this A, if it is true, then I am getting B. If it is false, then I am getting C. Okay, if it is false, so this is false and this is true. Then from B to C, I am getting D. Okay, so this is the control flow graph of a if block. So what will be the cyclomatic complexity? That is, suppose this if block is just a part of your large program. Suppose your program consists of 100 lines and this if block will contain 4 lines. So 96 lines are there left. So these 4 lines we have to complete. We have to compute the program complexity of these 4 lines. How to compute? For this code fragment if block. So how many E's are there? That is edges. Number of edges and number of vertices. How many?
4.
So 4 minus 4 plus 2, that is 2. Cyclomatic complexity is 2. What is predicate node? Predicate node means the decision making node. Here the decision making node is A. Why? Because from this node we can go either in this way or we can go in this way. We can get either B or C. So here the number of predicate node is 1. So 1 plus 1, this is 2. The third rule, number of closed region plus 1. How many closed regions are there? Only one closed region is there. So 1 plus 1, 2. So in these 3 ways, we can get the cyclomatic complexity of this graph. Is it clear? This is the cyclomatic complexity. Now, for program complexity, we have to use the asymptotic notation. Okay. So asymptotic notation, there are 3 ways. That is worst case complexity, average case complexity, and best case complexity. Okay. For after devising an algorithm, we can have three cases. Suppose quick short. After designing the quick short algorithm, we can have 3 techniques: best case, average case, worst case. Okay. That is, worst case is, it is the TN. What is TN? Time taken for compute or complete your algorithm, where N is the input, number of inputs. That is maximum time of the algorithm for an input of size N. That is average case. It happens sometimes. Most of the cases in our real life, we can have the worst case complexity. So best case, it is just a cheat with a slow algorithm that works fast on some input. So this is the typical running time. So constant running time, if we put a graph, that is here N, that is the input size along x-axis, and along y-axis we have the growth of the function, that is fn, growth of the function. So your fast complexity is constant t1. After that, log n will be there. Log n is faster than t of 1. Then n log n, this is called the quasi-linear, n log n. Then we have n to the power k, that is polynomial is n to the power c, it is polynomial. So any polynomial algorithm n to the power c, where c is greater than equals to 1. Okay, so tn, this is linear, then n square, this is quadratic, n cube, this is cubic, and last one is the exponential, where n is the input size. So first one is there, log n is faster than your 1, then n is faster than log n. After that, n log n. Next, n to the power c, that is n to the power p, where p is greater than 1, that is your p, where this is polynomial, and exponential will be there, that is 2 to the power n. Any algorithm that have the complexity 2 to the power n, can you identify any algorithm? We have already
Sir, finding the substring of a string.
finding the substring Tower of Hanoi.
Sorry, sir. Tower of Hanoi.
Yes,
That is also.
that will also have a complexity of exponential time, that is 2 to the power n. So how to find out the complexity of Tower of Hanoi? So first write down the problem statement. Then from that problem statement, we have to devise the algorithm. From that algorithm, we have to find out the recurrence relation of the Tower of Hanoi problem. Then we have to solve the recurrence relation either by using master method, or by using substitution, or by using recurrence tree. So after applying these three techniques, we can get the solution of the recurrence relation, and that will yield the output. That will yield the complexity of Tower of Hanoi, 2 to the power n. That is fastest growing term. Okay, so we have already know that the big O, there are three techniques. There are three notations for asymptotic. There are three asymptotic notations for finding the time complexity of an algorithm. That is your big O, that is your big omega, and your big theta. Okay, big O, big omega, and big theta. Okay, so what is big O? Big O notation. Big O notation, that is so big O notation, that is Fn is big O. So here Fn is n and Gn is n square. So which one is faster? Gn is faster. Okay, so Gn is faster than Fn after a certain number of after a certain limit. That is after n0, your input size n0, your Gn will grows faster. Okay, than Fn. Fn is linear and Gn is quadratic. Right? So by definition, big O is that there exists some constant c. There exists some constant c, and n0 greater than 0, such that your Fn, which is greater than or equal to 0, which is less than or equals to some constant into Gn for all n greater than or equal to n0. So for this case, we can say that Fn is big O of Gn. Gn is faster growing term. Okay, and these are some techniques. These are some properties for big O notation while computing the complexity. So first, if Fn is half n square, then the complexity of Fn is order of n square. Why? The constant factors are ignored. Second property is that big O is the, so suppose it is a it is an expression, that polynomial expression, that n square plus 5n plus 3. Okay, so fastest growing term among this expression is n square. So big O is order of the fastest growing term, n square. Big O is transitive. So if f1 n is big O of f2n, f2n is big O of f3n, then f1 is big O of f3. Big O is multiplicative. Okay, big O is the highest power of n in any polynomial, in a polynomial in n. Okay, so big theta. So what is big theta? Big theta is the big theta. What do you mean by big theta? Big theta is that two functions are given, Gn and Fn. So there exists C1 and C2, and n0 greater than 0, such that your C1 into Gn, which is less than Fn, and Fn at the same time, it is less than some C2 into Gn. Then we can say that Fn belongs to in between Gn, C2 Gn and C1 Gn. Okay, so theta is called the type bound, big O is called the upper bound, and big omega is called the lower bound. And for lower bound, we can write, so if this is your Fn, and this is your Gn, this is your Gn, this is Gn, this is Gn, and this is your Fn. So we can say that Fn is greater than Gn after a certain input n0. After that n0, we can say that Fn grows faster than Gn. Okay, so that Fn is big omega of Gn. That is, it is the lower bound of Fn. So there are total 3 bounds: big O, big omega, and the tight bound big theta. This is upper bound, this is lower bound, and this is the tight bound. Okay. So how to find out the complexity of an algorithm? How to find out the complexity of an algorithm? This is the code fragment from line number 1 to line number 8. This is the algorithm. This algorithm at line number 1, n is equal to something. So using scanf statement, I am inserting some value to n. Okay. So read input from user, line number 1. Then sum is equal to 0, second line. Third line is that I is equal to 0. Fourth line, while your I is less than n. Okay, so from line number 4, I'm starting the while loop. Line number 5, so number is equal to read input from the user. So sum is equal to sum plus number. Line number 7, I is equal to I plus 1. And line number 8 is that mean is equal to sum divided by n. Okay. So what will be the complexity for this small algorithm? This is the algorithm. Okay. Algorithm is independent of any platform, any programming language. You can implement it C, C++, Java, Python. Okay. So what will be the time complexity in terms of your input size? We are mainly concerned about the time complexity. So what will be the time complexity? Any idea?
It will be linear, sir. Order of n.
Order of n. Order of n, right? So how to compute this time complexity? Why this is order of n?
Sir, because we are because i's value is continuously increasing.
Yes.
And it's checking it's compare only one time only. The number is added to one time only for each loop.
So
I mean
from
for each
line,
iteration.
yes. So from line number 1 to 3, line number 1 is constant, line number 2 is constant, line number 3 is constant. So for line number 1 to 3, it will take constant time. I is equal to 0, sum is equal to 0, n is equal to 5. Let the user input is 5. So for line number 1 to 3, this is constant 1. Now while line number 4, it denotes while I less than n. So your I, it iterates over n times. Okay. So I less than n, so it will be n plus 1. Starting from the initialization and up to n. It is from initialization up to n, that is after the checking. So it will contain n plus 1. Line number 5 to 7, 5, 6, 7. These 5, 6, 7, this comes under this fourth line while loop. That is, it will run for n times. And line number 8, this is just a constant operation. That's why its time is constant, 1. So 1, 3, this is 3. 3 plus 1, 4 plus 1, 5. That is the constant is 5. Okay. The constant is 5. And why 4n? Why 4n plus 5? 5 is just 3 lines, 1, 1, 1 plus 1, 4 plus 1, 5. Why 4n is there? Tn is equal to 4n plus 5. So this is the recurrence relation. Tn is equal to 4n plus 5. This is the recurrence relation of your code fragment, of your small algorithm. Of your algorithm, this is the recurrence relation. Tn is equal to 4n plus 5. From this recurrence relation, we can easily compute the complexity that is order of n. Why? Because of ignore the constant term, so it will become 4n. Now ignore the constant factor, so the complexity is order of n, that is big O or big omega or big theta. It is better to say that it is order of n, that is linear time. So why 4n? Can you identify why this is 4n?
Sir, because line 5, 6, and 7 take n, and also line 4 take n.
Yes. So 5 to 7, these 3 lines will take 1 n, 3n plus line number 4, it will take 1 n. That is total 4n plus 5. Is it clear? So this assignment statement, the complexity will be order of 1. In a single loop, it will contain order of n. Any 2 nested loop, the complexity will be order of n square. Okay. So another single loop, I is equal to 0, I less than n into n, I plus plus, sum is equal to sum plus I. Why the complexity is order of n square? Can you justify your answer?
The
So
loop
because
is
the upper
running
limit of the loop is
for n square
Is running
times.
n square times. Number 7, constant time with the loop. The loop is for loop, but the complexity is order of 1. Why?
Because at the constant time, I will go up to until n to the power 5.
Yes, this is constant time. Okay. So suppose your algorithm contains these some lines. For I is equal to 0, I less than n into n, I plus plus, sum is equal to sum plus I. K is equal to 0, k less than n, k plus plus, sum is equal to sum minus, this will be k, okay? Sum minus k, and print sum is now sum. So for these 2 lines, mainly this line, the complexity is order of n square. For this line, the order is n, and this is just a printing statement. That's why constant term. So complexity of this code segment, n square n 1. Now according to the rule, the complexity of your algorithm, this will mainly focus for the highest growing term. Here the highest growing term is 1 is constant, okay, then n linear, then quadratic. Quadratic is fastest growing term. If we put n is equal to 2, then order of n, this one will give you 2. This will give you 2, but this will give you 4. If we put 3, it will give 3, but it will give from 4 to 8. Okay, if we put 4, this will 1, 2, 3, 4 in a linear fashion, but it will be quadratic. That is 4, then 8. Okay, in this way. So consider so Fn is log n and Gn is 10 to the power 10 to the power 10 to the power 10. I'm claiming that Fn is big O of Gn. Is it true or false? Any idea? Anyone? Am I audible to you? Fn is log n and Gn is 10 to the power 10 to the power 10 to the power 10. So Fn is big O of Gn. Is it true or false? Any idea? Any answer is accepted. But please interact. Anyone? So this is false. Why this is false? Can you justify? Getting no response.
So, because Gn is constant.
That's because Gn is constant. While comparing any two functions, any three functions, any n number of functions, that is comparing means you are just inserting the asymptotic notations over the function. That is either it is sum to two functions. One function is lower bound of another, one function is upper bound of another, one function is tight bound of another. So while you are comparing any two functions, you have to just be sure that these two functions are function of n, where Gn is a constant and Fn is log n. So Fn is big O of Gn. So it shows that Gn is fastest storing term. It is upper bound of Fn. It is false because 10 to the power 10 to the power 10 to the power 10. This is a constant term. Okay. So which one will be the correct answer? If it is false, so which one will be the corrected version? This is constant. This will be big omega. Fn is big omega of Gn. Is it clear to everyone? Is it clear?
No, sir.
No, sir.
Can you explain the last part?
Suppose your Fn is log n. Log n. And your Gn is some constant. 10 to the power 10 to the power 10. Okay. Now, if we plot the graph, this is your input size n, and this is your growth of the function. This is growth of the function. Okay, growth of the function. Now, Gn is constant. What will be the constant line? Gn is some constant. That is, this is constant. This is a graph for constant.
Yes,
and
sir.
This is log n. So log n is slower than log n. This log n is lower than n. This n is lower than n square. This is lower than n cube. This is lower than n to the power p, which is lower than your 2 to the power n. Your 2 to the power n is less than n factorial. So log n, this is a function of n. So log n, this is a log n function. So if we choose this is your n0, if we choose this is your n0, then this is your Fn log n, and this is a constant, that is your Gn. So which one is faster? After a certain time, after a certain input, input size n0. Which one is faster? Log n or any constant value? Which one is faster?
Sir, can you please repeat the
শুনতে পেলাম না।
বলছি স্যার একটু রিপিট করুন কোয়েশ্চেনটা।
If n is log n and gn is some constant, you can put 15 10 over 10, 10 to the power 10 to the power 10 up to 15 times. But this is still a constant, not a function of n. This is still a constant. So that's why this is a constant line. This is the constant line, and this is your fn, that is log n. So which one is faster? It is clear that fn is faster with input size, increasing input size n. So that's why fn is big omega of gn. Gn is the lower bound, it is not the upper bound. In your question, it is said that fn is big of gn. So it is just, that's why this is false. So complexity of first n positive number, 1 plus 2 plus up to n, 1 plus 2 plus 3 up to n. What will be the complexity? Formula is n into n plus 1 by 2. That is n square plus n. So what will be the complexity? Fastest growing term, and ignore all the. So in a polynomial of n, we have to choose the fastest growing term and we have to ignore all the constant. So from this n square plus n divided by 2, we can get order of n square is the complexity. Is it clear? First one.
Yes, sir.
Second one, n factorial. N factorial, we can write 1, 2, 3 up to n minus 1 into n. This is the formula for n factorial, right?
Yes, sir.
Now, this is less than, there are n terms, 1, 2, 3, 4 up to n minus 1, n minus 2, n minus 1, n. So this 1, it is less than equals to your n, your 2 less than equals to n, 3 less than equals to n, n minus 1, this is less than equals to n, and for last term n, this is less than equals to n. So we can write 1, 2, 3 up to n, this is less than n into n into n up to n terms. Can we write this? Just these two lines.
Yes, sir.
Can we write
Yes,
this?
sir.
So n
Yes,
into
sir.
n into n up to
Yes, sir.
n terms. So the formula is n to the power n. The formula is n to the power n. Suppose 2, 2, 2 up to n terms. We can write 2 to the power n. That's why n into n into n into n up to n terms. We can write n to the power n. So n factorial, this is less than n to the power n. So that's why you can say that your n to the power n, it is the upper bound of n factorial. So if this is fn and this is gn, after a certain input size n0, we can say that n to the power n, it will grow faster than n factorial. That's why n factorial is big of n to the power n. Is it clear? Second one.
Yes,
sir.
sir.
Yes, sir.
Now log n factorial is n log n. Very easy. From 2 we can get n factorial is big of n to the power n. So if we take log in both sides, we can get log n factorial. Now n log n. So log n factorial is less than n log n. So we can say that n log n is the upper bound of, log n factorial. Similarly, log 5n factorial, it is equals to big O of n to the power n. 2 to the power n, this is big O of n factorial. How to write? 2 to the power n is equal to 2 into 2 into 2 up to nth term, okay? Which is less than equals to 1 into 2 into 3 up to n terms. That is n factorial. So 2 to the power n, this is big O of n to the power n. So 2 is less than equals to 1. For this particular case, this is false. But for the second one, this is less than equals to, this is less than equals to 2, less than equals to 4, 2 less than equals to 5. And last nth 2, this is also less than equals to n. That's why we can compile this question in factorial, into n factorial, okay? Root 2 whole to the power log n is equal to big O of root n. How to write? We know that root 2n, root 2 whole to the power log n, okay? That is 2 to the power half. We can write this 2 to the power half. Root 2 is equal to 2 to the power half. Now 2 to the power half log n. So according to logarithmic property, this is log n to the power half. Now the formula is a to the power log b base x is equal to log to the power x to the power log b base a. So that's why we can write this is n to the power half. Is it clear? This number 8, everyone?
Yes, sir.
Number 9. How to show number 9 is true? Any idea? Anyone?
Sir, because 3 is bigger than 2 for each multiple.
3 is greater than.
Yes, sir.
That is 3 by 2. This is 1.5. That is greater than is equal to 1. 3 greater than 2. If we take x in both sides, so we can say that this. Okay. So this is the rank. Rank the following functions by increasing order of growth. This is the Corman's exercise, Corman's second edition most probably. And this is Corman third edition exercise. Okay. So from these functions, we have to rank the fastest growing term. So this is the increasing order of growth downward. Okay. So among these functions, these are the functions. Okay. Among these functions, 10 to the power 100, this has the lowest growth. Why? Can you justify? 10 to the power 100, this has the lowest growth. Why?
It's a constant.
Constant.
Yes, as this is constant. Suppose this is 10 to the power 100 to the power 1000 to the power 1 lakh. This is also have the same. That is, this is also constant. Okay. Next one is log n. Log n. So log n and log root log n. Log root log n. Both have the same time complexity. These two functions, log n and log root log n, these both have the same complexity. Can you justify why? This log root log n, we can write log n to the power half. Okay, both are order of n. That's why these two have same growth function. Next, log n is faster than log n. So actually, log n, this log n is faster than log n. LG means base 2 or 10. LG, ln means log base e. LG means log base কত হয় LG? 2 or 10. That is 2. LGN, it is greater than LG, LGN. Okay, so that's why LGN, this is faster than log n and root log n. But LGN and 1 over k runs from 1 to n. Why these two have same growth function? Because, do you know why? Why these two have same growth function? Very easy. If we expand this series, just expand this series, we can get the log n term. That's why log n and 1 over k runs from 1 to n, have same complexity. 5 root n and root 2 log n, these two have same complexity. Why? Root 2 log n, root 2 log n, root 2 log n, this is root n. Why? Because root 2 log n, we can write 2 to the power half log n, that is 2 to the power log root n, that is root n. Why 2 to the power log root n equals to root n? Do you have the answer? Any answer? Anyone? এবার কিছুই বলে না, চুপচাপ। স্বরাজ 32।
স্যার এলজির বেসটা 2 আছে আর 2 এর পাওয়ারে এলজি টার্মটা আছে তাই।
A to the power log b base x is equal to x to the power log b base a. That's why 2 to the power lg root n, we can write root n whole to the power lg 2 base 2. Now lg means 2 base, so lg 2 base 2 is 1. That's why this is root n. So root n, root 2 to the power log n, this is root n. Now here root n is equal to root n and root 2 whole to the power log n. These have same growth of function, ignoring the constant term 5. Okay. Now log n factorial and n log n, we already deduced the formula n factorial. This is same as n log n. Now n square and 4 to the power log n have same. Why? 4 to the power log n. N square and 4 to the power log n. Just because of 4 to the power log n, 2 square log n, that is 2 to the power log n square, that is n square. Okay. NC2. Why NC2 is equals to 8n square? Not equals to, this is same growth function. N square, 8n square, and NC2 and 4 to the power log n. Why they have same growth function? Any idea? Anyone? If we expand this NC2, we can get n factorial divided by 2 factorial into n minus 2 factorial.
Sir, overall equation of NC2 will be n into n minus 1 by 2. So
Yes,
overall complexity will be n square.
Yes, that's why this is n square. Overall complexity is n square. Now n cube is faster than n square. N to the power log n and 2 to the power log square n. this will have fastest growing term than n cube, 2 to the power n, and summation nck, these will have same complexity. If we expand nc0 plus nc1 plus nc2 plus nc3 up to ncn, we can get 2 to the power n. This is the simple formula. 3 to the power 2 to the power n, this is slower than 3 to the power n. That's why 3 to the power n is the upper bound of 2 to the power n. Now 3 to the power n, we know that 3 to the power n, this is less than n factorial. N factorial is the highest growing term, then n minus 1 factorial, then 3 to the power n. Why 3 to the power n? This is less than n minus 1 factorial, just because of 3 to the power n means 3 into 3 into 3 up to n terms, which is less than n 1 into 2 into 3 into 4 into up to n minus 1 factorial. That's why 3 to the power n, it is big O of n minus 1 factorial. This is the upper bound. Similarly, n factorial is the upper bound of n minus 1 factorial. So this is the arrangement of the growth of the functions. So our first chapter is complete. That is how to compute the complexity, and the order of the ranking order of the functions. Okay. Now, the second one, that is the recurrence relation. So the recurrence relation, there we have three types of recurrence relation. First one is the substitution method, second one is the recurrence tree, and third one is the master method. So substitution method, that is we have to substitute. Let Tn is equal to T of n minus 1 plus 1 for all n greater than 1, Tn is equal to 0, or all n less than equals to 1. So first I am writing Tn is equal to Tn minus 1 plus 1. Next, substitute this Tn minus 1, that is n minus 2 plus 1 plus 1, n minus 3, 1 plus 1 plus 1. So what is the base case? Base case is the basis step is the T1, that is after n minus step, n minus 1 step, that is Tn minus n minus 1, 1 plus 1 plus 1 up to n minus 1. So T of 1 plus 1 plus 1 plus 1 up to n minus 1. So from this second part, we can get n minus 1, and from the first part I am getting T of 1. Now T of 1, this is T of 1 when n is less than equals to 1, this is 0. So that's why first term is 0 and n minus 1 is the output. So what is the complexity? The complexity of this recurrence relation is the order of n. Here I am using big theta, order of n. So similarly, if we put this is n instead of 1, so Tn is equal to T of n minus 1 plus n, where n is greater than 1, and T of n, here this will be 0 for n less than equals to 1, and in the next problem, Tn is equal to 1 for all n greater than 1. Now the complexity will become order of n square. Why? Because using substitution method, Tn is equal to T of n minus 1 plus n. So next one, n minus 2 plus n minus 1 plus n. So n minus 2, n minus 1, n. So in this way, I am getting the basis step T of 1. So T of 1 plus 2 plus 3 up to n minus 2, n minus 1, n. So T of 1, the condition given that T of 1 for n is equal to 1, we can put 1. So 1 plus 2 plus 3 up to n minus 2 plus n minus 1 plus n. So sum of n natural numbers. So n into n plus 1 by 2. That's why complexity is order of n square. So is it clear? Question number 1 and 2.
Yes, sir.
Now similarly, question number 3 and 4, these are very similar. Question number 3 and 4. 3 means Tn is equal to T of n by 2 plus 1, n greater than 2. And the base case is Tn is equal to 1 for n is equal to 1. Question number 4, n by 2 plus n, and Tn is equal to 1 for n greater than is equal to 2 and n is equal to 1. So can you identify whose Which algorithm's recurrence relation is this? Can you identify? Question number 3 is a famous recurrence relation for an algorithm. Which algorithm is that? Anyone? The hints is that divide the problem into two parts and discard the other half. Now,
The binary search.
binary search. Very good. Binary search. So this is the recurrence relation for binary search. Okay. So this is the algorithm for binary search, and its complexity is order of log n. So binary search, it will depend upon the divide and conquer property. That is, first divide your problem of size n into two halves, each of size n by 2. So this is the problem size. New problem size is n by 2. Okay. So that's why the running time, how to compute the running time or complexity, that is Tn, where n is the input size of your algorithm. So Tn is equal to, first we divide the problem into two halves. That's why new problem size will now become n by 2. Next part is the we can discard any part. Okay, and again recursively solve the remaining half. Okay, so as we discard the other half, so that's why the number of sub problems, how many sub problems are there? Number of sub problems is 1 at each step. That's why 1 into n by 2 plus I'm finding only particular one element, binary search, searching for a particular element. Okay, so that's why the toll function, I'm discussing the toll function shortly. The toll function of this recurrence relation is 1. So this is 1 because of discarding the other half, and this is toll function, this is 1 because I am searching for a particular value out of a given array. Okay, so this is the recurrence relation of binary search. Now you can apply either substitution method, or you can apply the master theorem. Master theorem is very suitable for this type of recurrence relation, or you can use the recurrence tree method also. Okay, now for quick short and merge short, what will be the recurrence relation? Can you justify? Quick short, merge short, these are all depending upon the divide and conquer strategy. So divide and conquer strategy means divide, conquer, and next combine. Divide your problem of input size n into sub problems. Okay, then conquer part. Conquer means we have to find out the result using some recursion. So conquer means we have to find out the solution recursively. Okay, that is recursively we have to divide our sub problems. Okay, next combine. Combine, this part is hidden. Combine, that is finally I am conquering all the sub problems, so we have to jot down the solutions to get the final result. So this is your combined state. So this combined state, this division and combine, these will lead to a cost. This hides in a function that is called a toll function. This toll function, it encompasses the cost of dividing, conquering, and combining the elements. Okay, so that's why master theorem, it will have the form Tn is equal to A into T of n by B plus Fn. This is the master theorem form. Master theorem is suitable only for this format. We know that Tn is the running time of the algorithm. Tn is equal to Atn by B. Atn by B plus Fn. This is the only master theorem's form. So if your recurrence is in the form, then only we can apply the master theorem. Here the binary search, it is in the form this, because here A is equal to 1, here B is equal to 2, and Fn is equal to 1. Fn is the toll function. If this Fn is called the toll function, which encompasses the cost of division, conquering, and combination of your elements. Okay, so here this is 1. Why toll function is 1? Because I am searching for just one element. That's why this toll function is 1. Okay, now what will be the recurrence relation for quick short and merge short? Any idea? Anyone? Okay, so complexity for binary search. What will be the complexity for binary search? Anyone?
So log n.
So log n is the complexity for binary search. Okay. So this is the recurrence relation for binary search, and here n is equal to 2 to the power n. So capital N is equal to log n. Now we substitute the value. Tn is equal to 2 to the power n. I am substitute this n as 2 to the power n. So 2 to the power n is equal to n by 2. So 2 to the power n by 2. That's why 2 to the power capital N minus 1. Okay, this is the substitution method. Plus 1. So next step, if we substitute this 2 to the power n minus 1, we can get 2 to the power n minus 2 plus 1 plus 1. Again, substitute this value 2 to the power n minus 3, 1 plus 1 plus 1 up to nth term 2 to the power n minus n. So 1 plus 1 plus 1 up to n, up to nth term. So this 1 plus 1 plus 1 plus 1 plus up to nth term, this will lead to your n summation is capital N, and 2 to the power n minus n, this will 0. So 2 to the power 0 is equal to 1. So 1 plus capital N, that is 1 plus log n. That's why complexity is order of log n. So using the substitution method, I am getting order of log n. Is it clear? The recurrence relation of binary search, and from this using substitution method, I am getting the solution. Eta বোঝা গেছে? Is it clear? Is it clear to you? The substitution method for binary search.
Yes, sir.
Next, this is the recurrence relation for quick sort and merge sort. 2t n by 2 plus n. So using the substitution method, n is equal to 2 to the power n. So using the substitution method, we get 1 plus n. So 1 plus n, that is order of n log n. So quick sort and merge sort, these have the complexity order of n log n. And for binary search, this is order of log n. So why 2t n by 2 plus n? Just because of, in case of quick sort and merge sort, both halves are, in case of these two sorting, we have to divide the array into two parts, okay? And both halves are equally essential, equally necessary to find the final solution, okay? So that's why Tn is equal to, the new subproblem size is n by 2 with respect to the original problem. That's why T of n by 2. Two halves are essential. In case of binary search, one half is sufficient. So that's why 2 into n by 2. Plus, here in binary search, the toll function is 1 because I am searching for only one particular element. That's why 1. But here, in case of quick sort and merge sort, we have to deal with n number of elements. That's why toll function is n. So 2t n by 2 plus n. Is it clear why the recurrence relation for binary search of is this and for quick sort merge sort is this? Is it clear?
Yes, sir.
So if we apply the substitution method, in this format, So this is very easy. I'm getting the complexity is n log n. N log n, okay? Now these are some other substitution method examples. So Tower of Hanoi. Now range transformation, very important for your purpose. Range transformation. What is range transformation? So range transformation is that suppose the recurrence relation is given in this form, Rn is equal to A into R of n minus 1 plus Dn. Okay, this is equation number 1. Then to transform this recurrence to the fundamental recurrence relation, we have to use the range transformation. So the fundamental recurrence relation Sn is equal to, the form is Sn is equal to S of n minus 1 plus Dn. Okay, so this is the form. These are the fundamental form. These are the fundamental form. These are the fundamental form. Tn is equal to T of n minus 1 plus n, some control function n. This may be a function of n or this may be constant. Here in the first example, this is constant. In the first example, this is constant. In the second example, this is n. In the third example, this is again constant. Fourth example, again, this is n. Okay. Now, so this is the fundamental recurrence relation. Now we have to define Sn is equal to Rn by An. So Rn by a to the power n. Thus S0 is equal to R0. So I'm using a recurrence relation. Let Tn is equal to 2t n minus 1 plus 1. Can you justify which algorithm has this recurrence relation? 2t n minus 1 plus 1. Anyone? This is very interesting. Do you know the Tower of Hanoi problem?
Yes, sir.
So, in case of Tower of Hanoi, so how to implement the recurrence relation and how to get the solution from this recurrence relation. This is the main essence of algorithm. So Tn, Tower of Hanoi, Tn is this is the running time for Tn, running time of Tower of Hanoi. So first, in case of Tower of Hanoi, if you recall the problem, we can move T of n minus 1. We can move first, in the first step, we move the n minus 1 disk from source to the auxiliary using destination. Then we move the largest disk from the source to the destination using the auxiliary. And then again, we have to move the n minus 1 disk that resides at the auxiliary to the destination using the source. So Tn is the running time for moving n disk. So that's why T of n minus 1, this is the running time for moving n minus 1 disk from your source to the auxiliary using destination. Next, T of 1, I'm just writing 1. Okay, T of 1 is 1. This is my base case. T of 1, that is moving the time taken for movement of the largest disk from source to destination, T of 1. And again, moving the remaining n minus 1 disk from auxiliary to the destination. So finally, this will be 2t n minus 1. 2t n minus 1, 2t n minus 1, 2t n minus 1 plus 1. Okay, so this is the recurrence relation. Now we have to solve this recurrence relation. This is very important. T of 1 is 1. This is the base case. Okay. Now divide both sides. Now Tn is equal to 2t n minus 1 plus 1. Can we apply the master theorem here? No. Why? Because master theorem is applicable only for this format. T of n is equal to A into T of n by B plus Fn. So master theorem can't be applicable in this way, in this form. So divide both sides by 2 to the power n. So this is your a to the power n. Range transformation. So divide both sides by a to the power n. Actually, this is your range transformation. So minus 2 to the power n Tn. So this is 2 to the power minus n minus 1 into T of n minus 1 plus 2 to the power minus n. Just divide both sides by 2 to the power n. We can get this formula. Then Sn, let Sn is equal to this left hand side, 2 to the power minus n Tn. So Tn is equal to 2 to the power n Sn. So we can get Sn is equal to S of n minus 1 plus 2 to the power minus 1. Okay. So this is the fundamental recurrence form. Is it clear? This is the fundamental recurrence form. This is your fundamental recurrence form. Sn is equal to S of n minus 1 plus Tn by An. So this is Sn is equal to S of n minus 1 plus 2 to the power minus n. This is your fundamental recurrence relation. Okay. Now multiply both sides by 2 to the power n. So 2 to the power n Sn, 2 to the power n is n minus 1, 1. Now substitute this S of n minus 1. That is S of n minus 2, S of n minus 3. Finally, we can get 2 to the power n minus 1. Okay. So 2 to the power n Sn is equal to 2 to the power n minus 1. So Sn is equal to 1 minus 2 to the power minus n. Now Sn and Tn, what are the relationship? Tn is equal to 2 to the power n Sn. So Tn is equal to 2 to the power n Sn. That's why Tn is equal to 2 to the power n minus 1. So this is the recurrence output of the recurrence of the Tower of Hanoi. Now, can you justify the complexity of Tower of Hanoi problem is exponential? এটা বলতে পারবে এবার? Can you justify the answer? Tower of Hanoi will take huge amount of time because it will have the exponential time complexity. If n number n is 64, it will take the lifetime of your earth. If n is 64, it is very fast and it will take a huge amount of time to solve this recurrence relation, that is Tower of Hanoi problem. So why why the complexity of your Tower of Hanoi is exponential from this recurrence relation? Can you identify? Identify করতে পারবে? What is the complexity? What is the complexity of this recurrence relation? The complexity of this recurrence relation is 2 to the power n, ignoring the constant term, that is minus 1. The complexity of this algorithm of this Tower of Hanoi, its recurrence relation is 2 to the power n. Is it clear to everyone? Is it clear?
Yes, sir.
So that's why its complexity is order of 2 to the power n. So this is the substitution method. Okay. Now the recurrence tree. What is recurrence tree? So solving the recurrence using the recursion tree. Okay. So let the example is that Tn is equal to 2t n by 2 plus n, whose recurrence relation is this? Which algorithm? Quick sort, merge sort. Okay. 2t n by 2 plus n. Now we can divide this n into two parts, that is t of n by 2 plus t of n by 2. 2t n by 2, that is dividing this problem into two parts. One branch will contain t of n by 2, another branch will contain t of n by 2. again n is divided into n by 2, n by 2. So this n by 2 can be divided into two parts, n by 4, n by 4. Again, this is n by 4 and n by 4. So up to this division, so first Tn is divided into this step. Again, successive division, we will get T of n by 4, T of n by 4, T of n by 4, T of n by 4. 4 T n by 4. Okay. So if we divide this up into successive order, we can get the final leaf. At the leaf node, we will have the 1 1 1 up to n ones. So the height of this binary tree, this is log n. Height of this binary tree is log n. For the first line, the cost is order of n. For the second line, 2 into n by 2, that is 2 and 2 cancels out, we will get n. In the third line, there are 4 n by 4 operations, that is cost is 4n. In the last line, there are n ones, that is 1 1 1 up to n, that is n. So what will be the complexity of this recursion tree? The complexity of this recursion tree is the height. Just compute the height. How to compute the height? The height is order of log n into height into the cost for each step. Cost for each step is n. So n into height, that is n log n. Is it clear? This is the recursion tree. Here, in this problem, number 4, this is the recurrence relation for quick short, merge short. Using substitution method, I am getting the solution order of n log n. Here in the recurrence tree method, again I am getting the complexities order of n log n. Is it clear to you? That this is Tn is equal to T of n by 4 plus T of n by 2 plus n square. Okay. So n square is divided into two parts, n by 4 and n by 2. So n by 4 square, n by 2 square. So n by 4 square, that is, again, this is divided n by 16, n by 8. This n by 2 is divided into 4 and 2, that is n by 8, n by 4. So ultimately we can get 1 1 1 up to n terms of ones. So this is we have to find out the height of the recurrence tree and multiply cost of each step. Okay. So here Cn, this is divided into two parts, Cn by 2, Cn by 2. Here again Cn by 4, n by 4. So cost is Cn. At each step, the cost is Cn. At the last step, here n number of C will be there. That's why Cn, height is log n. That's why Cn log n plus Cn. So this is the recurrence tree method. Any doubts regarding recurrence tree method? Substitution method and recurrence tree method. Any doubts? Anyone? কারোর কোনো queries আছে? The substitution method and recurrence tree method. Now we will discuss the master theorem. The master theorem will have the form Tn is equal to Atn by B plus Fn, where Fn is the total function, okay? And A is the number of subproblems and N by B is the size of the subproblems, okay? Now, this will have total 3 cases. The first case is that we have to compare at every step we have to compare n to the power log b base a, n to the power log b base a with Fn. Every time we have to compare these two factors, n to the power log b base a and Fn, total function. So if your total function is greater than n to the power log b base a, that is fn, we can say that your fn, it is fn is equal to, we can say that fn is equal to big O of n to the power log b base a, n to the power log b base a, lg b base a minus epsilon. If we write this minus epsilon, okay, then your a minus epsilon, that is your n to the power log b base a is higher. So we have to subtract something from n to the power log b base a so that I am getting fn. So n to the power log b base a is higher, faster. So Tn is equal to, this will be order of n to the power log b base a. Suppose the recurrence, it will have the form, suppose the recurrence of the form Tn is equal to 2t n by 2. Let this is 2t let this is let this is 90 n by 2 n by 3, 90 n by 3, 90 n by 3 plus n square. So what will be the complexity of this Tn? What will be the complexity of this Tn? That is n to the power log b base a. N to the power log b base a means n to the power log 3 base 9, n to the power log b base a. That is, this is n cube. And your total function is order of n square. So which one is faster? N cube is faster. So you can express fn as n cube minus 1. So here your epsa value is 1, right? So a to the power 3 minus 1. That is, you can get order of n square. So the complexity will be, what will be the complexity? Sorry. N square. This will be n square. This will be n square, and let this is n. Let this is n. So n to the power log 3 base 9, that is n square, and your total function is order of n. So fn, this can be derived from n to the power log 3 base 9, that is n square minus 1. That is, this is your n. So the complexity will be order of n square. Now the second case 2. For case 2, if your fn is written, for the case 2, if your fn is written in this form, big theta of n to the power log b base a, n to the power log b base a into log to the power kn, into log to the power kn. If it is written in this form, then we can say that this belongs to case 2, and the complexity will be, what will be the complexity? The complexity of the algorithm will be Tn is equal to, we can say that Tn is equal to big theta of n to the power log b base a, into the power log b base a into log to the power k plus 1, into log to the power k plus 1, log to the power k plus 1 into n. So this is the formula Tn. So let one example. Tn is equal to t of n by 2 plus 1. T of n by 2. T of n is equal to t of n by 2. T of n by 2 plus 1. So can you identify which case it is? Can you identify which case it is? Case 1 or case 2? কোন কেসে এটা হবে বলো তো? আর ইউ গেটিং মাই পয়েন্ট? If you have any queries, please ask. এটা কোন স্টেপ কোন কেসে হবে? কেস 1 or case 2? Case 1 means n to the power log b base a, this is greater than fn. And case 2 means n to the power log b base a, it is equals to fn. কোন কেসে হচ্ছে? This belongs to case 2. Why? Because n to the power log b base a, that is log b base a means log 1, value of log 1 is কত হয়? log 1 এর ভ্যালু কত? Value of log 1, value
Sir,
of log
0.
1 is 0. So n to the power 0, this is equals to 1. And again your fn is also 1. So n to the power log b base a and your fn both are same. Okay. Now if we choose the k is equal to 0, then the complexity will be big theta of n to the power log b base a, that is n to the power 0, that is 1. And if we choose k is equal to 0, then 0 plus 1, that is 1. So LGN. So using binaries, using master theorem, this is the recurrence relation for binary search, t of n by 2 plus 1. Okay, the complexity will again theta of log n. Okay, so using substitution method, I am getting the solution order of log n. Using the recurrence tree, I am getting order of log n. Again, using the master theorem, I am getting the order of log n. The case 3, what is case 3? Third case. The third case says that your fn is greater than your n to the power log b base a. Your fn is greater than. If so, then it will become to the order of, in the third case, it will become to the order of, the growth function will lead to the order of fn. This is the third case. Any example of third case? Let this is n cube. Tn is equal to, let Tn is equal to 9t n by 3 plus n cube. Then n to the power log b base a, what will be the value? N to the power log b base a, then the n to the power log b base a will be n square, and n cube is the fn. Fn is greater than n square. So the complexity will be order of n cube. So using master theorem, we can also solve a recurrence relation, but there are some restrictions. That is, the form will have this, the master theorem will follow this particular form, atn by b plus fn. There are some pitfalls. That is, your fn, please notice this carefully, your fn is monotonically increasing function. Monotonically increasing your fn should be monotonically increasing or decreasing function. Monotonic function. That is, this is monotonic function. Monotonically increasing function. This is not a monotonically increasing. This function is not monotonically increasing, because at this particular point, this function is decreasing. Monotonically increasing means it will never decrease. Monotonically decreasing means it will never increase. So monotonic function, your fn is monotonic function. Suppose I am writing Tn is equal to 2Tn by 2. Suppose I am writing Tn is equal to 2Tn by 2 plus sin x, sin n. So can you solve this recurrence relation using master theorem? Your fn is sin n, sin function. Can you solve? Can you apply the master theorem? The form is 2Tn by 2. Okay, 2t n by 2 plus fn is sine n. We can't use this master theorem. Why? Because your sine function is not monotonic function. If we plot the sine function, it will have similarly sine function, cos function, it will have the negative part. It is not monotonic function. Monotonically decreasing, monotonically increasing, it will not have the monotonicity property. Okay, that's why the regularity condition breaks. So we can't allow fn is equal to sin x, cos x, etc. Okay, and here your a is a constant. Okay, here your a is a constant, and the value of a should be, here in master theorem, your value of a should be greater than equals to 1, but your b must be greater than 1. Your b must be greater than 1. Okay, so a is equal to greater than is equal to 1 and b must be greater than 1. Suppose it is given that your Tn is equal to 2 to the power n, T of n by 4 plus Fn is let n. Then can we apply the master theorem? No, we can't apply the master theorem because your a here your a is given as 2 to the power n. This is not a constant. Okay. Suppose your a is given 0.5. Tn is equal to 0.5. That is half. Tn is equal to half Tn by 2 plus n. Can we solve? No. Because a is greater than equals to 1. Your a value is half, 0.5. We can't apply the master theorem. 2 to the power n, it is not a function, it is not a constant. That's why not applicable. 0.5, this is less than that. That's why not applicable. Okay. Now, 2t n by 2 plus n log n. This is a special case of master theorem. We can't apply the master theorem here. 2t n by 2 plus log n, 2t n by 2 plus log n. We n log n. We can't apply the master theorem in this particular form. This is the special case of master theorem. Why? Because here fn by n to the power log b base a. What is your fn? Fn is equal to n log n. Your fn by n to the power log b base a. N to the power log b base a here. If we put n to the power log b base a, that is n. So this is equals to, we can get log n. Okay, this is log n. Now this log n is not asymptotically larger for n to the power. It is not, this log n is not asymptotically larger than n to the power epsilon for some constant epsilon greater than 0. That's why we can't apply this master theorem directly. So this falls into between case 2 and case 3. We can't apply the master theorem in this particular form. 2t, this is very important master theorem asked in any interview question. Suppose 2t n by 2 plus n log n. Can we apply the master theorem directly? No. Why? Because if n by n to the power log b base a, that is n log n by n to the power log b base a n, which is log n, this is not asymptotically larger than n to the power epsilon. Log n and n to the power epsilon, which one is faster, asymptotically larger? Which one is larger? Log n or n to the power epsilon? N or log n, which one is faster? N is faster, so that's why log n is not asymptotically larger than n to the power epsilon. Am I audible to you?
Yes, sir.
Yes, sir.
So this belongs to case 2, and so this particular formula, this particular recurrence, it falls under the gap between case 2 and case 3. It is not directly solved. So these are the some pitfalls for master theorem. So we have already discussed the asymptotic notation. And so 2 chapters are already discussed. Okay, binary search is discussed. Now quick shot and merge shot. So So this is so normal matrix multiplication. What will be the complexity for normal matrix multiplication? Any idea? Normal matrix multiplication. What will be the complexity? How many for loops are there? Do you know how to multiply two matrices in C? I'm not getting any response. This will just কোনো response পাচ্ছি না কিন্তু।
Sir, it will be order of n cube.
Order of n cube. Why? Because we are having 3 for loops. So this is the algorithm for normal matrix multiplication. Okay. So the complexity is order of n cube. But can you reduce this complexity? Yes, by using Strassen matrix multiplication. Now this Strassen matrix multiplication, this will depend upon the design strategy divide and conquer. Divide the subproblem, divide the problem into smaller parts, recursively solve, that is conquer the subproblems, and finally combine the result to get back the final result. This is the divide and conquer. So quick short, march short, Strassen matrix, binary search, these all depends upon this divide and conquer approach. Okay. So this is the algorithm for normal matrix multiplication. So C is equal to AB. Now the order of the multiplication is order of n cube, and the order of the addition n square into n minus 1. Okay. Now what will be the recurrence relation for matrix multiplication? How many additions are there? 1, 2, 3, 4. 4 additions are there. That's why 4, this should be 4n square. How many multiplications are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 multiplications are there. Okay. That's why 8t n by 2. So if the matrix have the size n by n, the subproblem, we have to divide the problem into subproblems. So if it have n by n, then the subproblem will be divided into n by 2. So the size of this subproblem is 2 by 2. So this particular element is 1 by 1, that is n by 2. So the problem is divided into 2 halves. Okay. And there will be total 8 multiplications. So 8t n by 2 plus c n square. Right? So if we apply the master theorem, then into the power log b base a, that is log b base a, that is we can get into the power log 2 base 8, that is n cube. And your total function, that is total function here, the total function is the addition. 4 additions are there. 4 additions, c n square is the addition. So n cube and n square, which one is faster? We know that n cube is faster. So it belongs to case 1. That's why the complexity is order of n cube. Now can you reduce? Yes, reduced. So Strassen matrix multiplication. Strassen discovered the 7 multiplication instead of 8 multiplication. Okay. We have total 8 n by 2 matrix multiplications. Okay. Here we have total 8 n by 2 multiplications. 1, 2, 3, 4, 5, 6, 7, 8. 1, 1, B1, 1. This is particular one element. This is 1, 2, 2, 1. This is another element. So there are total, so size of 1, 1, B1, 1. 1, 2, B2, 1. 1, 1, B1, 2. Size of this is 1 by 1. Okay, n by 2 size. So Strassen discovered total 7 matrix multiplications. So these are the Strassen's formula for finding the multiplications. I'm not going in detail with the Strassen's M1 through M7, total 7 multiplications are there. If A11, A12, 2122, B11, 12, 2122, these are the 2 matrices, then multiplications, total 7 multiplications will be there. Okay. And 1, 2, and there are total 7 multiplications and 10 addition subtraction will be there. Total 10 addition subtraction will be there. Okay. So finally we have total 7 multiplication and 10 plus 8, total 18 addition and subtraction. 1, 2, 3, 4, 5, 6, 7, 8. Total 8 addition subtraction in C11, C12, C21, C22, and here total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total 10 addition subtraction are there. Okay. So equation number 1 has total 7 multiplication, 10 addition, subtraction. Equation number 2 has total 8 addition, subtraction. So finally, the recurrence relation will become 7t by 2 plus 18a in square. Now, if we solve using Master theorem, or you can use substitution method, we can get the solution 2 to the power n to the power 2.81. So the complexity of matrix multiplication is getting reduced to 2.81 from 3. Is it clear? The matrix multiplication, complexity of matrix multiplication. In any interview, it is common question that can you reduce the matrix multiplication's complexity? Yes, we can reduce by using Strasson's matrix multiplication. This depends upon the divide and conquer strategy. So you have to remember these total 7 multiplications, M1 through M7. Okay. In these multiplications, we have total 10 addition subtractions, and these are C11, C12. This is the summation matrix. This is the final matrix, the multiplication matrix. C11, C12, C21, C22. Okay. So total 18 addition, subtraction, 7 multiplication, which will lead to complexity. If we solve the recurrence, we can get order of n to the power 2.81. Okay. Is it clear? Is it clear to you? Now, quick short. We know that quick short, this is the quick short algorithm. In case of quick short algorithm, this depends upon the divide and conquer approach. Okay. Any queries regarding the Strassson matrix? Anyone? Any queries? Okay, I think no queries are there. So quick short, this depends upon the binary, this depends upon the divide and conquer approach, quick short APR. So if P is less than R, we can partition. This is quite obvious. This is first index. This is the last index. So Q is equal to, first we have to partition this array. So A, P, Q minus 1. This is the first array subarray. This is the middle one, and this is the last one. P to Q minus 1. This is Q, and Q plus 1 to R. Then the partition function. Here we are using the Lomoto partitioning. That is the last element as the pivot. Okay. So last element is our X. So first index is P, last index is R. Okay. Now I is equal to P minus 1 and J is equal to P to R minus 1. If AJ is less than your pivot, then I is equal to I plus 1 and exchange AI, AJ. Finally, AI plus 1 and AR are exchanged and return I plus 1. So I am using an array 2, 8, 7, 1, 3, 5, 6, 4. Okay, so this is your array. Now, the first index is P, the last index is R, right? Now, I is equal to P minus 1. That's why I is described here, out of bound. I is equal to P minus 1. And J runs from P to R minus 1. This is your J. J runs from P to R minus 1. Okay. Now, 2. What is your X? X is your AR. Your last element is chosen in Lomoto partitioning as pivot. In Hoare partitioning, the first element is chosen as pivot. In randomized quickshot, any element is chosen as pivot. Here I am discussing the Lomoto partitioning, that is last element as pivot. So here 4 is the pivot, that is X is equal to AR. Now your first element, whether J runs from P to R minus 1, if AJ is less than X, so 2 is less than 4. So 2 is less than 4. Then what should I do? So first we have to increment I. So I is equal to I plus 1. Then exchange AI with AJ. So now your AI is 2, your AJ is 2. I is incremented by 1. That's why 2, this is AI, this is AJ. So 2 is exchanged with itself. Okay. Your pivot is 4. Next, J is increased by 1. So this is your J. Okay. And I is pointing here. Now, whether your J is less than 4, no, your J is not less than your pivot. So increase your value of J. That is J will be at this point. 7 is less than 4, no. So increase J. Your I resides at that particular point. Now 1 is less than 4. Yes, 1 is less than 4. So what should I do? If AJ is less than is equal to X, first we have to increase I, then exchange AI at AJ. So 1 is less than equals to 4. Very good. Then first increment I. So I will be now at this position. AI will be 8. Okay. Then exchange AI and AJ. So replace AI with AJ. That is 8 and 1 are exchanged. That is 1 will be there, 8 will be there. Okay. This is the interchanging operation. So next increase J. So 5 and 4. So 5 and 4. Now J at 5 and R at 4, X at 4. So 5 is greater than 4, so increase J. So J 6 is greater than 4, so stop. J will run at R minus 1. So after that, in exchange AI plus 1 and AR. So your entire line 3 to line 6 computation is done, running from P to R minus 1. Now 7 is exchange AI plus 1 and AG. AI plus 1 and AR. So we have to exchange. That is, I is at 3. So I plus 1, that is 8. So interchange this 8 and 4. So 4 will be there, 8 will be there. So basically, finding pivot means we have to find this pivot and we have to place the pivot in the array in such a way that some elements are less than equals to your pivot, some elements are greater than your pivot. So that's why this is the divide and conquer strategy. So 4 is placed here. So all the elements are less than equals to 4, all the elements are greater than 4. Again, we have to recursively solve this left subarray and right subarray. And finally, this is the solved array 1, 2, 3 up to 8. So this is the quick sort. And the complexity of quick sort. What is the complexity of quick sort? What is the complexity of quick sort? Do you know? What is the complexity? So the recurrence relation is that worst case complexity is that. Why worst case? Worst case is that if the problem is already, if the array is already shorted, this is the worst case scenario of quick sort. Okay. So we have n is the subproblem. So already shorted means one subproblem will have no element, another one is n minus 1. Again, if we divide n minus 1 into two parts, that is 0, n minus 2. Again 0, n minus 3. Okay. So the recurrence relation will have t of n minus 1 plus t of 0 plus theta of n. Theta of n is the total function. So finally t of n minus 1 plus theta of n, we can get order of n square. The complexity is order of n square. The best case, why best case? Best case is that if it is balanced, that is recurrence relation t of n by 2 plus theta of n, that is n log n. This is the quick sort algorithm. Okay. So I think the time is I'm reaching the end time. So any queries regarding the divide and conquer strategy? This 2 hours is very insufficient to cover these problems. So today we have discussed about the algorithmic complexity, the recurrence relation, and divide and conquer approach. So any queries? from your side?
No, sir.
Okay, so these are the rest of the problems. So quick shot is already discussed. And for March shot, this is your March shot algorithm.
Sir,
Yes.
sir, can you share the Word file with us? Means where the topics are present.
Yes, sir. And the document which you have shown, like the written one.
Okay, but your group.
Sir, you can mail us our group mail ID. We can give you the group mail ID.
Okay, just put your group mail ID in the chat box.
Okay, sir. Sure.
For both the section.
Okay, sir. Sure.
Now this is the March shot. Here, this March shot is also it depends upon your divide and conquer strategy. APR, your A is first argument array, then your P is the first index, just like quick shot, and R, this is the last index of the array. So if P is less than R, just in quick shot, this is quite obvious. If first index is less than last index, so we have to find out the middle point. Q is equal to P plus R divided by 2. Then again we have two parts, left part and right part, left subarray and right subarray. So left subarray, the arguments are A, the array, the first index, and the last index for the left subarray is Q. For the right subarray, the first index will be obviously Q plus 1, and last argument is R. Then we have to call the merge function. This merge function is described here. What is the merge function? This is your merge function. Okay. So here, this is the merge function N1 and N2. What is N1 and N2? N1 and N2, this depends upon divide and conquer strategy. That's why we have to divide the whole array into two subarrays. First subarray size is N1, second subarray size is N2. Q minus P plus 1, R minus Q. Okay. So create two subarrays. L is equal to 1 to N plus 1. R 1 to N2 plus 2. So for I is equal to 1 to N1, we have to copy the left portion of your given array to the left array, Li. We have to copy the right portion of the given array to Rj, that is right array. Now here the array is 1 to N1 plus 1 instead of 1 to N1. Similarly, right array is 1 to N2 plus 1 instead of 1 to N2. Why? Because the last index are called the sentinels. These are the guard. These are denoted as infinity. Okay. In your program, you can put 999 or any huge number. Okay. In your C program, any flag can be denoted as your sentinel, guard of your first subarray and second subarray, left subarray, right subarray. Now we have to compare I is equal to 1, j is equal to 1. For k is equal to p to r, if any index of your left subarray is less than any index of right subarray, then we have to copy the left subarray to final array and increment the value. Otherwise, copy the element from right subarray to the final array and increment j. So this is the array. Okay, 2, 4, 5, 7, 1, 2, 3, 6. This is the array. So our first task is to divide this whole array into two subarrays. Okay, and first left subarray, it will have n1 number of elements. It will have n2 number of elements. Okay, so 2, 4, 5, 7, infinity. This is the sentinel. Similarly, 1, 2, 3, 6. 1, 2, 3, 6. This is the right subarray, and this is the sentinel. Okay. Now, how to compare? Up to this. This is complete. Now, from I is equal to 1, j is equal to 1, k starts from p to r. If compare li and rj, so compare these 2 and 1. Which one is smaller? 1 is smaller. So 1 will be put it here. So this case, that is else part, Rj is copied into AK and J increment the value of J. So increment the value of J. J will now be at this position. Now 2 and 2, which one is smaller? This is says that if Li is less than Rj, so copy Li to Lk and increment I. So copy this Li to 2. This 2 is placed here, original array, and increment this value 4. Now compare this 4 and 2. Which one is smaller? 2 is smaller. So copy this 2 here. So copy this 2 here. Increment this value 3. 3 and 4. Which one is smaller? 3 is smaller. So copy this 3 here. So copy this 3 here. Okay. Again increment 6 at 6. So 6 and 4. 4 is smaller. 4 put here. 5 and 6 put 5 here. 7 and 6 put 6 here. And finally 7. Put 7 here. So this is the shorted array. This is actually the merge sort. Okay, and this is the recurrence relation for your merge sort. This is the recurrence relation for your merge sort. 2t n by 2 plus theta n. Okay, 2t n by 2 plus theta n. This is the total function. Okay, and this is the. Now, two halves are equally required. That's why A value is 2 and B value n by B. That is, subproblem size is n by 2. At each step, we have to recursively divide the whole array. Okay. So this is the merge sort. The complexity of merge sort is again same as quick sort n log n. But worst case, best case, average case for all, this is n log n. But in case of quick sort, the worst case is order of n square. So it is very important in any interview question that can you identify the worst case situation of quick sort? It is commonly asked question in any interview. Worst case scenario of quick sort. Then we have to say that worst case means your array is already shorted. So if the array is already shorted, then we can have only one element in left side array, another n minus 1 element in the right side. Okay, so one element, that's why partition is 0. So n we can get 0 n minus 1, n minus 1 is divided 0 n minus 2 up to 2 0 1. Okay, so this is the cost, and if we compute the height, we can get order of n square. So this is your merge sort and Strassen matrix multiplication are discussed. Okay. So asymptotic notation, solving of recurrence, divide and conquer. Why? One important question: why the algorithm is called greedy? Can you justify why this is greedy? What is the definition for greedy? In any interview question, you will be asked why this is called greedy. Greedy means the algorithm will always find the local optimal instead of global optimal. Hope in the mind that I will ultimately find the global optimal. This greedy may not always yield the optimal solution. It will always try to find out the local optimal, not the global optimal. But hope in the mind that I'm finding the global optimal. But the greedy will not always yield optimal solution, whereas dynamic programming always gives you the optimal solution. Dynamic programming সব সময় optimal দেবে, but greedy may not always yield the optimal solution. Okay. So, okay. So these are the groups, right?
Sir, for CSCB, it is the RIMA which